Welcome to today's session. We're going to tackle an interesting problem from LeetCode titled Assign Cookies. This problem involves distributing cookies to children in a way that maximizes happiness, which is both a fun and practical exercise in algorithm design. Let's dive in and explore the problem in detail. In this problem, we are tasked with assigning cookies to children to maximize the number of satisfied children. Each child has a greed factor, which represents the minimum size of a cookie that will satisfy them. Similarly, each cookie has a specific size, and a cookie can only be assigned to one child. A child is considered satisfied if the size of the cookie they receive is at least equal to their greed factor. The inputs to this problem are two integer arrays, one representing the greed factors of the children and the other representing the sizes of the cookies. Our goal is to calculate the maximum number of children that can be satisfied with the given cookies. For example, if we have 3 children with greed factors of 1, 2, and 3, and 2 cookies of size 1 each, how many children can we satisfy? Let's look at some examples to understand this better. Here's our first example. The input consists of greed factors g equals 1, 2, 3 for 3 children and cookie sizes s equals 1, 1 for 2 cookies. The output is 1, meaning only one child can be satisfied. Why is that the case? Well, the first child, who has a greed factor of 1, can be satisfied with one of the cookies of size 1. However, the second child, with a greed factor of 2, cannot be satisfied because the remaining cookie is not large enough. The third child, with a greed factor of 3, is also left unsatisfied for the same reason. Therefore, only the first child is satisfied, and the maximum number of satisfied children is 1. Now, let's look at another example. Here, the greed factors are g equals 1, 2 for 2 children, and the cookie sizes are s equals 1, 2, 3 for 3 cookies. The output is 2, meaning both children can be satisfied. The first child, with a greed factor of 1, can be satisfied with a cookie of size 1. The second child, with a greed factor of 2, can be satisfied with a cookie of size 2. There's even an extra cookie of size 3, but it remains unassigned since there are only 2 children. This example shows how efficient allocation of cookies can maximize the number of satisfied children. Let's consider one more example to further clarify. Here, the greed factors are g equals 3, 5, 7 for 3 children, and the cookie sizes are s equals 2, 4, 6, 8 for 4 cookies. The output is 3, meaning all 3 children can be satisfied. The child with a greed factor of 3 can be satisfied with a cookie of size 4. The child with a greed factor of 5 can be satisfied with a cookie of size 6. Finally, the child with a greed factor of 7 can be satisfied with a cookie of size 8. Notice that the smallest cookie, of size 2, cannot satisfy any child and remains unused. By matching the cookies to the children in the most efficient way, all the children are satisfied. To summarize, this problem comes with constraints and edge cases that need to be considered. For example, if there are no children or no cookies, no one can be satisfied, and the result is 0. If all the greed factors are larger than all the cookie sizes, again, no child can be satisfied. On the other hand, if each greed factor exactly matches a cookie size and the arrays are of the same length, all children can be satisfied. When there are more cookies than children, some cookies may remain unused, but the number of satisfied children is dependent on the number of children. Similarly, if there are more children than cookies, some children will remain unsatisfied, and the allocation must be done efficiently to satisfy as many children as possible. These considerations help ensure that our solution is robust and handles all possible scenarios effectively. To begin, one approach we could consider is the brute force method. The intuition here is straightforward. For each child, we try every possible cookie to find the smallest one that meets their greed factor. This ensures that each child gets the smallest cookie that satisfies them, aiming to maximize the distribution. The process involves iterating over the list of children and, for each child, searching through the entire list of cookies to find a suitable match. While this approach guarantees correctness, it's important to recognize its inefficiencies. Specifically, the time complexity is O(n) squared, because of the nested loops, and although the space complexity is minimal at O(1), the computational cost of iterating through each combination makes this approach impractical for large input sizes. Additionally, it doesn't take advantage of sorting, which could significantly simplify the process. Overall, while the brute force method is conceptually simple, it becomes highly inefficient as the problem scales. Now, let's consider a more efficient solution with the optimized greedy approach. The key insight here is that by sorting both the children's greed factors and the cookie sizes, we can systematically assign cookies in a way that minimizes waste and maximizes the number of satisfied children. With both lists sorted, we can use 2 pointers, one pointing to the current child and the other to the current cookie. The process works as follows: if the cookie at the current pointer is large enough to satisfy the child's greed factor, we assign it, and then move both pointers forward to handle the next child and cookie. If the cookie is too small, we simply move the cookie pointer forward to find a larger one. This approach is efficient because it avoids unnecessary comparisons, and the sorting step, which runs in O, n log n, dominates the time complexity. With no additional data structures needed, the space complexity remains O(1). The greedy approach is not only faster but also elegant in its simplicity, making it ideal for larger inputs where brute force would falter. Ultimately, the chosen strategy is the optimized greedy approach, as it strikes the perfect balance between efficiency and simplicity. The pivotal realization is that sorting both the greed factors and cookie sizes enables us to assign the smallest cookie that satisfies each child, ensuring maximum satisfaction with minimal effort. Using 2 pointers further reduces the need for redundant comparisons, making the solution both time and space efficient. The brute force method, while correct, is computationally expensive with O(n squared) complexity and becomes impractical for larger datasets. By contrast, the greedy approach leverages sorting to streamline the process, and though sorting adds a pre-processing step, the overall efficiency gain far outweighs this cost. Additionally, the greedy strategy is grounded in the assumption that satisfying children with smaller greed factors first leads to the best outcome, which aligns perfectly with the problem's constraints. In conclusion, this method not only scales well but also maximizes the number of satisfied children in the most practical way possible. The problem asks us to distribute cookies to children in a way that maximizes the number of content children. Each child has a greed factor, which specifies the minimum size of the cookie that can satisfy them, and each cookie has a size. To solve this, we need to assign cookies optimally so that we waste the least amount of resources. The first step is to sort both arrays. Sorting the greed array ensures we handle the least demanding children first, while sorting the cookies array allows us to assign the smallest cookies that meet the children's needs. This minimizes waste and helps us systematically approach the problem. After sorting, we use 2 pointers, one for the greed array and one for the cookies array. These pointers start at the beginning of their respective arrays, allowing us to iterate through both simultaneously to compare the greed factor of the current child with the size of the current cookie. This setup forms the foundation of our approach to solving the problem efficiently. Now, we begin iterating through the arrays using the 2 pointers. While both pointers are within the bounds of their arrays, we check if the current cookie can satisfy the current child. If the size of the cookie is greater than or equal to the child's greed factor, the child is content, so we increment the pointer for the greed array to move to the next child. Regardless of whether the child was satisfied or not, we always increment the pointer for the cookies array to consider the next cookie. This ensures that we progress through the list of cookies and try to match each with the next child in need. At the end of the iteration, the value of the pointer for the greed array tells us how many children have been satisfied, as each increment of this pointer represents a content child. This simple yet effective process ensures we assign cookies optimally while minimizing unnecessary comparisons. This approach works because it leverages the principles of a greedy algorithm. By always assigning the smallest possible cookie to the least demanding child, we maximize the number of satisfied children. The 2-pointer technique is key here, as it allows us to traverse both arrays efficiently, comparing only what is necessary. The overall time complexity is O(n log n), driven by the sorting step, while the 2-pointer traversal itself runs in O(n). It's also important to consider edge cases. For example, if either array is empty, no children can be satisfied, so the result is 0. If the smallest cookie is still smaller than the least greedy child's factor, no children will be satisfied. On the other hand, if there are more cookies than children, the excess cookies are simply ignored, as we only care about matching cookies to children. These insights highlight why the algorithm is both efficient and robust. The core data structures in this approach are arrays and pointers. The greed and cookies arrays are sorted in place, which minimizes space usage since no additional structures are required. The 2 pointers enable linear traversal, ensuring that each child's greed factor and each cookie size are considered exactly once. Arrays are particularly well suited to this problem because they allow efficient sorting and direct access via indices, which are essential for implementing the greedy strategy. In terms of complexity, the sorting step dominates with a time complexity of O, n log n, where n is the length of the larger array. The subsequent traversal with the 2 pointers is O, n, making the overall time complexity O, n log n. Space complexity is O, 1, since we sort the arrays in place and do not use extra memory-intensive structures. This combination of efficiency in both time and space makes the algorithm an excellent solution to the problem. This Python solution tackles the LeetCode problem number 455, assign cookies by implementing a greedy algorithm. The goal is to maximize the number of children who can be content with the given cookies. Step-by-step explanation. 1. Sorting asterisk. First, the greed array, representing the minimum cookie size each child needs, and the cookies array, representing available cookie sizes, are sorted in ascending order. Sorting ensures that we can try to match the smallest available cookie to the least greedy child first, which is key to the greedy approach. 2. Initialization asterisk. 2 pointers, child_i and cookie_j, are initialized to 0. These pointers help track the current child and cookie being considered during the iteration. 3. Iterate through arrays asterisk. The while loop continues as long as there are children and cookies left to consider. If the current cookie _j, is large enough to satisfy the current child, greed, child_i, the child pointer, child_i, is increment to move to the next child, signaling that the current child is content. Regardless of whether the cookie satisfies the child or not, the cookie pointer, cookie_j, is increment to move to the next cookie. 4. Return result asterisk. When the loop ends, the value of child_i represents the number of children who have been satisfied, as each satisfied child increments this counter. Complexity. Time complexity asterisk sorting takes O, n log n, for both the greed and cookies arrays, where n is the maximum length of the 2 arrays. The subsequent iteration through the arrays is linear, O, n. Thus, the overall complexity is O, n log n. Space complexity asterisk. The solution uses constant extra space, O, 1, as it operates directly on the input arrays after sorting. This approach guarantees an optimal solution by greedily trying to satisfy the least greedy child with the smallest available cookie, ensuring no resources are wasted. This is the Java implementation of LeetCode problem number 455, assign cookies. The solution mirrors the logic of the provided Python code. Both the greed array and cookies array are sorted in ascending order. 2 pointers are used to iterate through each array. If a cookie satisfies a child's greed, the child pointer moves forward, and the cookie pointer progresses regardless. The implementation uses Java's arrays.sort for sorting and adheres to Java conventions with explicit type declarations and class structure. In this first example, we are given a list of greed factors 1, 2, 3, and a list of cookie sizes 1, 1. Both arrays are already sorted, so we begin by initializing 2 pointers, child_i to track the current child and cookie_j to track the current cookie, both starting at 0. During the first iteration, we check if the current cookie, which is of size 1, can satisfy the first child's greed of 1. Since 1 is greater than or equal to 1, the first child is satisfied. We update child_i to move to the next child and cookie_j to move to the next cookie. In the second iteration, the next cookie of size 1 is checked against the second child's greed of 2. Since 1 is less than 2, this cookie cannot satisfy the child, so we only increment cookie_j to move to the next cookie. However, there are no more cookies left to check. At this point, the pointer cookie_j equals the total number of cookies, which signals the end of the loop. The number of satisfied children is stored in child_i, which is 1, meaning only one child was content with the given cookies. The output for this example is therefore 1. Now, let's examine a second example where there are more cookies than needed. Here, the greed factors are 1, 2, and the cookie sizes are 1, 2, 3, both already sorted. As before, we initialize child underscore I and cookie underscore j to 0, preparing to iterate through the lists. In the first iteration, we check if the smallest cookie, which is of size 1, can satisfy the first child's greed of 1. Since 1 is greater than or equal to 1, the first child is satisfied. We increment both child underscore I and cookie underscore j to move to the next child and the next cookie. In the second iteration, we see if the next cookie, which is of size 2, can satisfy the second child's greed of 2. Again, 2 is greater than or equal to 2, so the second child is satisfied. Both pointers child underscore I and cookie underscore j are increment again. Now, child underscore I equals the total number of children, which terminates the loop. Since both children were satisfied, the output is 2. Now consider a third example where the cookies are insufficient to satisfy the greed of any child. The greed factors are 3, 4, 5, and the cookie sizes are 1, 2, both sorted. We initialize child underscore I and cookie underscore j at 0 as usual. In the first iteration, we check if the smallest cookie of size 1 can satisfy the first child's greed of 3. Since 1 is less than 3, this cookie cannot satisfy the child, so we increment cookie underscore j to check the next cookie. In the second iteration, we see if the next cookie of size 2 can satisfy the first child's greed of 3. Again, 2 is less than 3, so this cookie also cannot satisfy the child. We increment cookie underscore j once more, but there are no more cookies to check. At this point, the pointer cookie underscore j equals the total number of cookies, and the loop ends. Since no cookies were able to satisfy any child's greed, the value of child underscore I remains 0, indicating that no children are content. The output for this example is therefore 0. This demonstrates how the algorithm efficiently handles cases where no solution is possible, as it simply iterates through the cookies until no further matches can be made. This concludes our walkthrough of the solution. To analyze the time complexity of our solution, let's break it down step by step. First, we need to sort both the greed array, which represents the children's greed factors, and the cookies array, which contains the sizes of the cookies. Sorting the greed array takes m asterisk log m, where m is the number of children, and sorting the cookies array takes n asterisk log n, where n is the number of cookies. Together, these sorting steps contribute m asterisk log m plus n asterisk log n to the overall complexity. After sorting, we iterate through the arrays using a two-pointer approach. In the worst case, the while loop runs a maximum of max m n times, as we either exhaust all the children or all the cookies. Each iteration involves simple comparisons in pointer increments, which take constant time. Hence, this step contributes m plus n. Combining both parts, the total time complexity is m asterisk log m plus n asterisk log n plus m plus n. However, since m asterisk log m plus n asterisk log n dominates m plus n, the overall time complexity simplifies to m asterisk log m plus n asterisk log n. When we combine the sorting step and the iteration step, the overall time complexity of the solution is dominated by the sorting step, resulting in m asterisk log m plus n asterisk log n. This remains true across all scenarios best, average, or worst case, because the sorting step is always required. For the best case, even if the arrays are already sorted and every child can be satisfied without evaluating all the cookies, the sorting step still contributes m asterisk log m plus n asterisk log n. For the average and worst cases, where more evaluations are needed during the iteration, the additional work is still overshadowed by the sorting step, so the complexity remains m asterisk log m plus n asterisk log n. Now, onto space complexity, the solution is highly efficient in terms of memory usage. Since sorting operations, such as timsort in Python, are typically performed in place, no additional memory is required for the sorting. Apart from the input arrays and a few integer variables like child underscore I and cookie underscore j used for the two-pointer iteration, there is no extra memory allocation. This means the auxiliary space usage is constant, making the overall space complexity 1. To understand why the optimized approach is more efficient, it's helpful to compare it to a brute force method. A naive solution would involve checking each child's greed factor against all available cookies to find a match. This would require iterating through all combinations of children and cookies, resulting in a time complexity of m asterisk n, where m is the number of children and n is the number of cookies. In contrast, the optimized approach sorts both arrays first and then uses a two-pointer technique to find matches. This reduces the problem to a linear pass through the arrays after sorting, resulting in a significantly better time complexity of O, m asterisk log m, plus n asterisk log n. To break this down mathematically, sorting an array of size k takes O, k asterisk log k, so sorting the greed in cookies arrays contributes O, m asterisk log m, plus n asterisk log n. The two-pointer iteration runs at most max, m, n, times, which is linear and adds O, m plus n. However, since O, m asterisk log m, plus n asterisk log n, dominates O, m plus n, the total time complexity is O, m asterisk log m, plus n asterisk log n. This optimized approach is clearly more scalable for large inputs compared to the brute force method. In this section, we'll explore some common mistakes that can occur while solving the assign cookies problem and how to avoid them. One frequent mistake is neglecting to sort the arrays. Sorting the greed factor array and the cookie size array is essential because it ensures that each child is assigned the smallest available cookie that satisfies their greediness. Without sorting, the allocation process becomes inefficient and incorrect. The fix is straightforward: always sort both arrays before proceeding with the allocation logic. Another common issue arises from implementing the greedy assignment without properly moving the pointers. Failing to advance the pointers for both children and cookies when a child is satisfied may lead to repeatedly checking the same cookie, which disrupts the process. Using two pointers and incrementing them correctly solves this problem. Lastly, some may attempt to match cookies to children using nested loops. While this approach may seem intuitive, it results in O, n squared, complexity, which is impractical for large inputs. Instead, leveraging a greedy approach with two sorted arrays brings the complexity down to O, n log n, making it much more efficient. Now, let's consider some additional pitfalls to watch out for. Overlooking edge cases is a common oversight. For instance, what happens if there are no cookies available, if all the cookies are smaller than the smallest greed factor, or if there are more cookies than children? These edge cases can lead to unexpected behavior if not handled properly. The solution is to test thoroughly with a wide range of scenarios to ensure your implementation is robust. Another mistake is modifying arrays mid-iteration, such as using pop or slicing to remove elements. This can cause index mismatches or unintended side effects, making the logic harder to follow and prone to bugs. Instead, rely on pointers or indices to traverse the arrays without altering their structure during the process. When it comes to interviews, it's important to recognize this as a classic greedy algorithm problem. Interviewers often want to see if you can identify when a greedy approach is appropriate and implement it efficiently. The key insight here is to minimize wasted resources by satisfying the least greedy child first. Sorting the arrays lays the foundation for this strategy. Aim for optimal complexity, which is O, n log n, due to the sorting step. Any higher complexity, such as O, n squared, could raise concerns about scalability in an interview setting. Communication is also critical. Clearly explain why satisfying the less greedy children first leaves more resources for the greedier ones. Additionally, be ready to discuss follow-up variations, such as handling shared cookies between two children, introducing a maximum limit on the number of cookies a child can receive, or adding constraints like cookie weights or priorities. These variations test your ability to adapt the core solution to new requirements. Looking at related problems can help solidify your understanding of greedy algorithms. The assign cookies problem is just one example. Another is the candy problem, where you distribute candies to children based on their ratings, ensuring fairness. The meeting rooms 2 problem involves allocating resources like meeting rooms based on scheduling constraints, which is another variation of greedy allocation. Similarly, the minimum number of arrows to burst balloons problem deals with minimizing resource usage to solve an interval-based challenge. Beyond these, alternative approaches to the assign cookies problem can also deepen your understanding. A brute force method, for instance, iterates through each child and checks all remaining cookies. While simple to implement, this approach is inefficient for large inputs. On the other hand, a 2-heap approach uses separate heaps for greed factors and cookie sizes, allowing dynamic allocation. While this can handle cases where new children or cookies are added during runtime, it's often unnecessary for static problems like this one. Lastly, let's discuss the binary search approach, which offers another way to solve this problem with a time complexity of n log n. After sorting the greed factors, you can use binary search to find the smallest available cookie that satisfies each child. This method can be particularly useful when the problem involves frequent queries or updates, as it allows for faster lookups. However, it is slightly more complex than the two-pointer approach and may not always be necessary for simpler variations of the problem. The trade-off here is between implementation simplicity and the flexibility to handle dynamic scenarios. By understanding these different approaches, you can choose the most appropriate one based on the problem's constraints and requirements. Great job! We've just solved the assign cookies problem using a greedy approach. Remember, sorting is a powerful tool in algorithm design, especially for problems like these. Keep practicing and exploring similar problems to strengthen your understanding. Thanks for watching, and don't forget to like and subscribe for more coding content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!